Hi folks. So we're working through the first of two examples. Um, this first one is a roller coaster problem. The problem reads, you are on a roller coaster with a large loop halfway through the ride. At the very top of the 20-meter radius loop, the 270 kilogram car, which includes the passenger's weight, or mass I should say, is traveling at 15 meters per second. What is the normal force from the rails on the car? So I really should have put that on there. What is the normal force from the rails on the car? So I would always begin by drawing a picture, right? So let's just increase our width a little bit here. So something very basic like that, right? I think in my notes I actually have us going from right to left. I'm going to change that up this time. I'm going to go left to right. So we come in from the left here, we go around our loop, woo, woo, right, and then out to the right. And our cart is just going to be a little square here with maybe, I don't know, a person. Woo! They're having fun. So our person here is going to be going tangentially with some speed of 15 meters per second. And we know that the radius of our loop here is 20 meters. So we are fully upside down in this problem at this point. We're right at the top of the loop. And I want to be very clear, if we zoom in and have these, our rails here, that is, kind of on top if we're treating, positive y as up. Our rails are on top of our car here. So when we're considering the normal force, if we're drawing a free body diagram at this point, I think, obviously we have our weight, mg, down, but I also think that we have some normal force down. The normal force isn't up because if we think about how we are kind of pressed against the surface of the rails are providing a force down on us. It's helping to keep us in the loop. I mean, another way of saying that is if I think about our rails here and my car, little wheels. Why would the rails pull me up? That doesn't quite make sense here. Unless I'm just kind of hanging, and then my wheels are somehow on top of this thing. We aren't given too many details here, but I think that this is a good assumption to make for our free body diagram. And if we're wrong, well, guess what? We'll get a negative normal force, and that negative normal force is going to tell us, boom, it's in the opposite direction. So right now, we know a couple things. We know our velocity, we'll write that over to the side here, is this way. And then our centripetal acceleration, well, the net acceleration here needs to be centripetal. I need to stay in this loop. And so I know that I need to have a net acceleration down, right, centripetally. So if I think about the sum of my forces here, we can take a snapshot and think about it actually just in x and y. Normally we've been kind of, with the previous example, working in r and theta, but let's just do x and y for a moment. It's a snapshot of this system. In the x direction, there are 0 forces because there's 0 net acceleration in the x direction. In the y direction, which is really secretly our radial, direction right now, we have two forces. We have our normal force and our gravitational force. I could write negative Fn minus mg equals m times negative ac. I could do that, but notice that there's a negative, 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 right? So I think what I'd rather do instead is just kind of preemptively throw that negative sign, divide by negative 1 or multiply by negative 1, however you want to do it, and say that Fn plus mg equals mac. If I do that, I'm really saying that Fn plus mg equals our m of the cart times v squared over my radius. Let's just move that up just a little bit. I know v. I know that tangential speed. I also know something about the radius. So if I want to know what the normal force is, Fn, I can subtract. I can pull out an m on both sides, or both terms here, and say m times my quantity of v squared over r minus g. Right? Plugging in some numbers, if I say 270 kilograms times 15 meters per second squared. That square should be on the outside. Got a little hasty. Divide it by the radius, which we said was 20 meters minus 9.8 meters per second squared. What do I get? I should get my normal force is 391.5 newtons. And we already said that if it was a negative number, my original assumption was actually wrong, right? It was going to be the normal force pointed up. But if we got a positive number, then we said, well, then our assumption was correct, and our normal force actually does point down. And that is exactly what we're seeing here. We have a positive answer. And so, and again, we were already considering the negative due to the direction. That all kind of came out in the wash because everything pointed down. So this positive number is kind of confirmation that the normal force does indeed point down. Our rails are pushing down on our car to keep us in this loop. So that is our roller coaster example problem. We see that this free body diagram really is just a snapshot. It's not a consistently rotating one, simply because our speed is actually going to change as we go through this loop. It violates our assumption that we made back in chapter 5 that we have a constant force everywhere. But for this snapshot, we can kind of get away with just looking at this moment in time. So that's this problem. If there are any questions, of course, please reach out either in an office hour or maybe ask a question in recitation or just email me about it. See you in the next one.